Today's topic is going to be trigonometric substitution, and we use this method when we encounter integrals that involve square roots that we can't solve in other ways using u sub. So we want to look at very specific forms of square roots. If we see anything that looks like this, a squared minus u squared, where a is a constant and u is a variable, we're going to make the substitution where u is equal to a sine theta. If we see the square root of u squared minus a squared, we're going to make the substitution where u is equal to a secant of theta, and we'll see why this works later. If you see the square root of a squared plus u squared, we're going to let u equal to a tangent of theta. So just keep these in mind. Let's take a look at an example and see how this works itself out. Let's assume that you encounter the following integral, 1 over x squared times the square root of 9 minus x squared dx. If you look at the form, it looks like the first one we see there, where it's a squared minus u squared, or a constant squared minus a variable squared. So we are going to look at a as equal to 3, and u is equal to x. According to what we said previously, we're going to let u equal a sine theta, which specifically is, in this case, x equals 3 sine of theta. Let's start to build the integral substitutions and see what it looks like. Let's look at what x squared looks like. X squared looks like 9 sine squared theta. And now let's also look at what 9 minus x squared looks like. If you make the substitution, 9 minus x squared looks like 9 minus 9 sine squared theta. And next, let's put that under a radical to see why this sort of substitution is good. So if we look at radical 9 minus x squared, that looks like radical 9 minus 9 sine squared theta. Let's factor out a 9, which becomes a 3, and we're left with square root of 1 minus sine squared theta. And we know that that is an identity. So we can replace the 1 minus sine squared theta with cosine squared theta. And amazingly, what happens is the radical goes away, and we're just left with 3 cosine theta. And that's the power of trig sub, is it makes radicals go away. So let's go ahead and make our substitution. For x squared, we're going to replace that with 9 sine squared of theta. And then the radical 9 minus x squared we saw earlier can be replaced with a 3 cosine of theta. The most common mistakes that students make is they forget to substitute for dx. Okay, so we actually need to figure out what that is. Well, if x is 3 sine theta, then dx is just going to be 3 cosine theta d theta, because you move the d theta over. So we need to put that in as well. That's very important that we don't forget this. Let's take a look at what this integral looks like now that I'm completely in theta land. So can we cancel anything out? Yeah, it turns out we can cancel the 3's and we can cancel the cosines. Okay, so here's what it looks like. Simplified, I can factor out the 1/9, and I'm simply left with a 1 over sine squared theta d theta. But that can also be written as 1/9 integral of cosecant squared theta. And we know the integral of cosecant squared theta. We know that its integral, based on our ideas of derivatives, is negative 1/9 cotangent of theta plus c. Now, if you stop here, you're actually not done yet, because remember that the original integral was in x land, but the current answer we have is in theta land. So we need a way to communicate between x land and theta land. And the way we're going to do that is we're going to look back at our original substitution and see if that unlocks the map to go from theta land back to x land. So originally we said that x was equal to 3 sine of theta. Let's rearrange that and view it as sine of theta equals x over 3. Now, because we know trigonometry, we know that this describes a right triangle. and sine is opposite over hypotenuse. So we know where to put these variables. So opposite is x and hypotenuse is 3, and by Pythagorean, you know that the adjacent side is 9 minus x squared. So now let's ask ourselves, what is cotangent? Cotangent is adjacent over opposite. So we can make that substitution and go back to x-land. So our final answer, if I write it in x-land, is negative 1/9, and that cotangent will get replaced with adjacent over opposite, and adjacent we have square root of 9 minus x squared, and opposite we have x. So this is actually our final answer because we've completely moved back to x-land. Let's look at the next problem, which seems fairly innocuous. And if you look at the form, it's going to look a lot like the third radical that we have on our list. So let's identify the different pieces. Our u squared is the part with the variable, and our a squared is the part that's just constant. So in this situation, a is square root of 3, and u is 2x. So we're going to make the substitution where u is equal to a tangent of theta. Let's go ahead and plug in what we know. So u again is 2x, our a is rad 3, and then there's tangent of theta. So let's go through the process. Let's start to build the square root and see what the pieces look like. So I need a 4x squared. Well, what does 4x squared look like? If we square what we have, 4x squared is going to look like 2x quantity squared, and then we add the plus 3. So 2x quantity squared is simply 3 tan squared theta plus 3. Let's put that under the radical. So square root of 4x squared plus 3 is really the square root of 3 tangent squared theta plus 3, according to our substitution. Let's factor out a 3 from the radical, which leaves me with tangent squared theta plus 1. And we all know that that's a Pythagorean identity, which is specifically secant squared of theta. And again, if we do this correctly, the square root should cancel out. And in this case, we're left with rad 3 secant of theta. Okay, so let's go ahead and make our substitution into the integral and bring it completely from x-land into theta land. But don't forget, we need dx. So to get dx, we're going to need to divide by 2. So x equals rad 3 over 2 tan theta. And when we differentiate, we get that dx equals rad 3 over 2 secant squared of theta d theta. So I'm going to take all these, substitute it in, and then I should be completely in theta land, and hopefully I can integrate that. So what does my integral look like? Let's first replace the dx, and the dx was rad 3 over 2 secant squared of theta d theta over, and that square root we now can rewrite as square root of 3 secant theta. Okay, let's simplify the integral a little bit, and then hopefully we can integrate it. So what does this look like simplified? Well, the square root of 3's cancel out, and I'm left with a 1/2 integral secant of theta d theta. The secant of theta is an integral that we've seen previously, but at this point in the class, it's probably best to just look it up in the table because it's not really relevant to derive it at this point. The integral of secant is 1/2 natural log absolute value secant theta plus tangent theta plus c. But again, this is completely in theta land, so I need to get back to x land. And the way I'm going to do that is I'm going to use our original substitution to get us back there. So originally, what we had said is that 2x is equal to square root of 3 tangent of theta. So if I rearrange that, I would get that 2x over rad 3 is equal to tangent of theta. This will allow us to draw a triangle where tangent is opposite over adjacent. So I know that 2x goes to the opposite, rad 3 goes into the adjacent, and by Pythagorean, the hypotenuse is the square root of 3 plus 4x squared, which showed up in the original problem, if you remember. So now I can go back to xland completely and by using this triangle. So if we go back to xland, our final answer is 1/2 natural log, and for secant, which is adjacent over, or hypotenuse over adjacent, I can replace that. The hypotenuse is square root of 3 plus 4x squared over the adjacent, which is square root of 3, plus tangent is opposite over adjacent. Our opposite in this case is 2x. Our adjacent is rad 3.